Today we're going to look at the derivatives of both sine x and cosine of x. We're going to leave the other trig functions for another time. We need a little bit more information before we can get to those, but we're really just going to focus our time right now on those two derivatives, as well as the derivative of e to the x. So we're going to build our understanding about sine of x, or the derivative of sine of x, and then just kind of apply that to the derivative of cosine of x and the derivative of e to the x as well. So here I have a graph of sine of x, and since we're looking for the instantaneous rate of change at every given point to be able to develop the graph of the derivative of sine of x, we're going to go ahead and just look at, we're going to kind of like approximate some tangent lines at key values. So notice at pi over 2, I have a horizontal tangent line, which means that the derivative equals 0 at pi over 2. I have a horizontal tangent line at 3 pi over 2 as well, which means, again, my derivative of sine x is 0 at that value. That happens again at 5 pi over 2. So we're seeing that this cyclic action that happens with trigonometric functions is also happening with its derivatives. If now I zoom in really close right here and I look at the tangent line at 0, it almost looks like a linear function the more I zoom in, right? And what we'll notice, and it's a little tricky given my x-axis, but what we would notice is that the slope of this line, of this tangent line, is actually equal to 1. And again, that's a little tricky with what we have given here to see, but you could also graph this in Desmos and see more specifically that the slope of this line is very close to 1 when we're approximating it. So I'm going to put that at 1. And then conversely at pi, the slope of the tangent line when x equals pi is going to be -1. And that continues on at all of those key values. So now I have 1, I'm going down to -1, then I'm going back up to 1 at 2 pi. And you'll notice that these are some key values that are very true for cosine. At pi over 2, notice I have another, or negative pi over 2, I have another slope of 0, right, for that tangent line. And so what we see, based off of our tangent line approximations, is that the derivative of sine is actually cosine. So we're going to go, actually I'm just going to write that up here for right now. So the derivative d dx of sine of x is equal to cosine of x. All right, now let's take this graph that we've just graphed and look at the derivative of cosine of x. I'm going to do that one in blue. All right, so following the same logic, notice that I have a slope of 0. I have a slope of 0 right here as well. And I would have a slope of 0 right there if I had kept that moving along. All right, and now at pi over 2, I have a slope of -1. So I'm going to bring that down here. And at 3 pi over 2, I have a positive slope. And that positive slope would be equal to 1. And so notice if I start to kind of connect these dots, or these points, that blue graph actually gives me my sine function, but reflected over the x-axis. So the derivative of cosine of x is going to be a negative sine of x. Let's go ahead and write those on our sheet. So at the beginning of the year, I told you to have a page in your notebook that was like towards the back, or that was like something that you could access if you were in good notes that you could access at any time. So go back and find that, pause the video until you find that. Right now, the only thing you have on there are special limits, memorize, and you have all of those limits written at the top. We're now going to add 2 more derivatives, the derivative of sine x and the derivative of cosine x. So like we just saw, the derivative of sine x is cosine of x, and the derivative of cosine of x is a negative sine of x. All right, the other one that's one of my favorites is the derivative of e to the x. And if we were to sketch this one out, or solve it algebraically, which normally we would do with the board if I were here, we would find that the derivative of e to the x is just itself. So following that same, it's a little bit harder to see, but if we were following that same kind of logic of kind of approximating those tangent lines, we would see that the derivative of e to the x is just itself, which is pretty cool. There's a lot of good memes online about the derivative of e to the x being like indestructible, because no matter what you do to it, it's just itself. Little math geek humor. All right, so again, you don't need to write this down, but I just want to kind of give you an example. If I were to take the derivative with respect to x of 5x subtract cosine of x, I would take the derivative of 5x, which would just be 5, and now I'm taking the derivative of cosine x. So I'm subtracting the derivative of cosine x is a negative sine of x, so I'd be taking a negative sine of x, so I would end up with 5 plus sine of x. So that's it. Same with e to the x. If I was taking the derivative of, let's say, 3 e to the x plus, we'll do 2 sine of x. The derivative of 3 e to the x, 3 is a constant multiplier, so we just leave that alone. The derivative of e to the x is just itself, so this stays 3 e to the x, plus 2 is a constant multiplier, just stays multiplied out front. Derivative of sine of x is cosine of x, and you're good to go. That's it. So you're going to go ahead and do a delta math just to practice these and to practice some more with the differentiability and continuity. And then there is a problem set for you to get started on in class and finish up for homework.